situations, and so I want to make sure that we kind of bring our mind back to relevancy here. It says a field goal kicker has 95% accuracy in his kicks this season. What is the probability that he makes exactly 4 out of his next 6 kicks? And so we're going to use a 0 for a make, and we'll use an X for a miss. So he's going to make 1, 2, 3, 4, and he's going to miss 2. Okay? And for him, that would be a bad stretch, right? Like he's not used to missing 2 out of 6 kicks because he's 5% accurate. So what is the probability that he makes it? 0.95. And we had that happen 4 times, so we raise it to the 4th power. And what is the probability he misses? 0.05. And we're going to square that. So recall that these need to add to 1, and that the 4 and the 2, that makes 6. And then we have a coefficient that goes out front, and that coefficient is going to be 6 choose 4. How do we calculate 6 choose 4? So, 6 times 5 times 4 times 3 times 2 times 1. Divided by 4 times 3 times 2 times 1 times 2 times 1. And so the 4 times 3 times 2 times 1, that cancels off. I get 30 divided by 2, which is 15. 15 is the number that goes up front. I go ahead and grab my calculator and I type that in.
Hey, Jens.
Yeah.
And another prediction thing here, would the distance of the field goal change the percentages?
Yes. So we're now taking that into consideration without a doubt. Yes, you could make this much more complicated. Would it be better to say free throw, 95% free throw shoot?
I didn't know that. I really didn't know that. I promise. Really, from the bottom of my promise.
I have 0.03.
It was raining. I get there.
Okay. There we have it. So I would expect that you could do a problem like that on the test, where you had a binomial situation. Binomial means that you have a success and you have a failure. Okay, and we put it together like that. So we bring this into light, boys. Okay, we're going to bring this into the light of what we're going to do, kind of moving forward here in class, which is this example. I decided to pick on myself here. By age 35, so guys, you're not far off from being in this boat as well. Approximately 60% of men experience significant hair loss. I actually reduced it. It's actually about 65% of men by the age of 35 experience significant hair loss. We have selected a random sample of 400 men between the ages of 35 and 38. This may not sound like a binomial distribution, but it is, because we're going to call success as, in this case, having hair loss, and not having hair loss as failure, which should seem like the other way around. But there are two situations. Either you have significant hair loss or you don't, one or the other. Guys, if you want to know the better chance that you could have significant hair loss, you would look at your grandpa on your mom's side. That's not a foolproof way, but that's a better indicator. Grandpa on your mom's side. Okay, that's a better indicator. So
Why is it? Is that just
it's just the genetics.
So your mom's dad.
Your mom's dad. It's not a guarantee, but that's a better indication.
I'm not wrong.
Okay. All right.
Is your mom's dad bald?
Oh, without a doubt, my mom's dad, his children, and actually my mom, even her hair is definitely thinner as she's gotten older. So without a doubt, I had no shot in it. So. Where was it? So here's what happens. Okay. Notice what's different here is that instead of having, like in the previous example, we had 6 kicks, right? Well, here we're selecting 400 people. That's a lot, isn't it? And when you start to select large numbers, We don't have to do that same thing anymore. We can do something else. It turns out that we can use a normal distribution. Remember, a normal distribution is a bell-shaped curve, right? We can start to use that when this number becomes significantly large. So, normal distribution of a binomial random variable, we can write this down. It turns out that suppose x has binomial distribution. Just like this example we see above, okay? Either you have a significant hair loss or you don't, okay? With n trials. In this case, we have 400 people that we're seeing. Do they have significant hair loss or do they not? When n, the number of trials, the number of people, becomes large, and we'll define what large is in a second, okay? The distribution becomes normal. And that's really good because we've already learned how to do kind of normal curve calculations. And so we're going to bring it back to that, and that's going to kind of be a foundation as we move forward in this class. What does it mean to be large? Here's what we're saying. The number of successes has to be greater than or equal to 10, and the number of failures has to be greater or equal to 10. Okay? So successes and failures have to be greater than or equal to 10. We would say that that's going to classify as large. And I want you to understand that in statistics, nothing is really that exact. But we do our best to try to make sure that we're being accurate in our what we're saying. And so I said the distribution becomes normal. It becomes approximately normal. The larger the sample size is, the more normal it becomes. And so we're better off that way. Okay? So how do we find the mean? Well, it's super easy. The mean is equal to the expected value. So suppose we have 400 men and 60% of them generally have significant hair loss. Then all we need to do to come up with the expected value is we just take whatever the probability is times the number of people that we're surveying. How do we determine the standard deviation? I won't go into how we derive this formula, but it turns out the standard deviation is equal to the square root of the expected value, which is NP, times 1 minus P. All these formulas I'll make sure I give to you on the test. I'll try to make sure that they are in your study guide packet tomorrow as well. But there is a problem here, and we're not going to dwell on it for a long time, but I want you to understand. So in that previous example, okay, the field goal kicker was kicking a field goal, right? 95% chance he makes it, right? And the next time he goes and kicks a field goal, it's kind of the same condition, isn't it? And then the next time it's the same condition. Kind of like when we were selecting things out of a bag for marbles, we pulled the marble out, and then once we pulled it out, we put it back in, right? Well, you can't take these people you take out. It's not like you could take one out and put it back in the field. That doesn't really work very well, does it? It's not like you're going to select one guy at random and then put it back in the field and then choose somebody else. You're generally choosing that 400 altogether. That can be kind of an issue, but it doesn't have to be. You don't have to go back and put the people back in. You don't have to go back and do the replacement if this is the case. When we sample, people and other things in the real world, we don't replace them. Meaning we don't put them back after selection, okay? This is not a problem. so long as your sample size is less than 1/10 of the population. So in this case, we really like the design. Either a guy has significant hair loss or he doesn't have significant hair loss, which makes it binomial. But the fact is that we're not replacing the guys after we select them. That's not a problem so long as our sample size is less than 1/10 of the entire population. So 1/10. So if I multiply 10, I get 4,000. Do you think that there's more than 4,000 men in the world? Yeah, so we're okay. You know what I mean? If our sample size was 4 billion, we'd be in trouble, okay? But it's 400, so we're okay, all right? So, I couldn't resist. I had to show, raise your hand if you took pre-calc with me last year, okay? Does that look familiar?
No.
Okay, especially my two calc people see it. We call this Pascal's triangle. This is actually the expansion of the binomial theorem. And so I'll generate it for everybody else so you can see. Pascal's triangle is simple. You put down a 1, and on the sides you always put 1, and then you add the previous two together. So 1 plus 1 is 2. You put a 1 and a 1. 1 plus 2 is 3, and 2 plus 1 is 3. Put down a 1 and a 1. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And we like to use that for a certain piece of mathematics. Calculus students and everybody else, it turns out that this number that goes in front, it's always a number from Pascal's triangle. So if you look here in this situation, notice that it is 6 choose 4. So if you go to that one that has a 6 power, choose 0, 1, 2, 3, 4, and there it is. Furthermore, look at what happens to our distribution. 252 in the middle, and then just 10 on the sides. Do you see that? So you can see as we continue to add these up, the curve is starting to do that, a normal curve. So it all comes together in kind of a unique way. So let's actually answer this problem. What is the probability, and this is what we want to focus on today, so when we asked in your assignment, what's the probability that more than 50% of men have significant hair loss of the 400 that we gathered? Okay? So we'll check for condition of sampling and bins on the next example. For this one, super easy. We first find the mean. All we do is we take mu is equal to n times p. In this case, mu is equal to n is the number of people we sampled. How many men did we sample?
400.
400. And what's the probability that each one has significant hair loss? So we multiply it by 0.6, and we get 240. Okay? So remember, in order for us to say it, we're going to use this normal distribution. 240 has to be greater than 10. Okay, number of successes. And then what would we expect would be the number that wouldn't have significant hair loss? 160, right? Because it would add up to 400. So these two are both greater than 10. So that's good news for us. We'll now calculate the standard deviation. Standard deviation, we say the square root of, and it just ends up being whatever n time p was, which was 240.
Yes.
Yeah.
What did you mean by when they're both greater than 10? Are you talking about the triangle?
So we have to be able to say that the number of successes and the number of failures is greater than 10.
Oh,
And I'm not going to trick you guys and give you guys situations where they're not. I just want you to know that theoretically, like, we need to make sure that there's more than 10 for each one. And there are, so we're good to go. In order to find your standard deviation, you take the mean, which is 240, and you multiply it by 1 minus p. What's 1 minus p? 1 minus 0.6 is 0.4. And we calculate that standard deviation. Go ahead and do it on your calculator. I got 9.797, You okay with that? I'll write 9.798. And so now we can do our z-score. Okay? We have z, remember, is equal to x minus the mean divided by the standard deviation. Okay? We're wondering the probability that more than 50% of people have significant, or these men have significant hair loss. So we're wondering the probability that, what would be 50% of our group? What's 50% of our group? 200. The probability that x is greater than or equal to 200. Okay? That's what we're wondering. So we're going to check that. We're going to take 200 minus our mean, which is 240, and we're divide that by 9.798. And so I have negative 40 divided by that 9.798. And I've got negative 4.08. Everybody got that? So negative 4.08. I got to go to my table of values. Let's find a z-score, negative 4. What do you guys notice?
It's off the table.
Yeah, it's literally off the table, isn't it? Okay? As you look here, everybody agree there's a very, 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 very small chance that the number of men who have significant hair loss is less than 200. It's almost guaranteed. Like if you were to draw this out, here's what it would look like in this scenario. So I go back to here, and I go back to my sheet. If you were to work this thing out, okay, 240 is in the middle. It turns out that 200 is over here, okay? So like over here is like 0.00001, and over here is 0.99999. We're almost 100% certain. That more than 200 men will have significant hair loss in that group. A number like negative 4.08, yeah, you're just about 100% confident. Okay, I'm going to try 2 with you, and you're going to try 1 on your own. Girls, only girls, raise your hand if you're left-handed. 1, 2, 3, 4. Okay, it said that approximately 10% of women are left-handed. Do you think that more guys are left-handed or more girls are left-handed? Guys, it's about 12% of the population for guys are left-handed, about 10% of the population for girls are left-handed. Okay, that's what it is. I don't know why, I haven't looked into it, but that's what it is. We have selected 140 women at random. What is the probability that more than 25% will be left-handed? Okay, I'm going to go ahead and find my mean. My mean is equal to, what is my sample size? 140 times, what is the chance that a woman is left-handed? 0.1, and when I multiply them, I get 14. So 14 needs to be greater than 10, right? And we're good. So that would be a success, is if they're left-handed. How many would be not success then? 126, right? So both of those are bigger than 10, so we're happy with that. So I have my mean. I now calculate my standard deviation. Standard deviation is equal to the square root of. I take my mean, which was 14, and I multiply it by what? 0.9. So we'll check that. 3.549. We have the two pieces that we need. Let's go ahead and figure it out. It says, what is the probability that more than 25% will be left-handed? So that's the probability that X is greater than 25%. Well, what's 25% of my 140? So we're running the probability that more than 35 people are going to be left-handed in that group. Okay? Let's check it out. Z is equal to X minus the mean divided by your standard deviation. Again, the number that we're testing is 35. So 35 minus, what is my mean? 14. Divided by 3.549. And we get 21 divided by 3.549. What'd you get?
5.92.
5.92. Let's look at our chart here. Do we have a 5.92? What decimal would you use to represent 5.92? 0.99999? Exactly. If we were to draw this out, here's what this would look like. You would have a normal curve, okay, where we said that this is, we're expecting it to be 14. And what are the chances that it is 35? Okay? Well, all of this, remember, whatever's on your table, that's the area to the left. So that would be 0.9999, okay? So what would you say about this area right there? It is very small, right? Almost no chance. Okay? We don't even have anything on our table in order to show it. I meant for that to happen in the previous example. I didn't mean for it to happen in this example. I quick did a wrong calculation. Tougher for me to come up with these problems on the fly than it is for me to come up with some of the other problems. But I don't think that these two work out in that kind of way. Approximately 41% of all first marriages end in divorce. We have selected 80 couples of newlyweds. What is the probability that more than at least 50% of them, okay, that more than 50% of them will eventually end in divorce, okay? Tell me what I calculate for my mean. Mean is equal to what?
40 times 0.41.
Yep, not 40, but 80. That's what population we selected times my 0.41. Somebody tell me what we get there?
32.8.
32.8. So we have 32.8 successes. So how many failures would we have? 47.2. Those are both above 10. That's good for us. Standard deviation is going to be equal to the square root of. I simply take the mean, which is 32.8, and I multiply it by 1 minus p. What is 1 minus p going to be? 0.59. I hope that this works out better. $4.399. So I want to know the probability that x is greater than what? Greater than 40. We want to know the probability that at least half of them will end in divorce, and half would be 40. So my z-score says z is equal to x minus the mean divided by the standard deviation. Or in this case, x is 40, that's what we're testing. We're going to subtract that from 32.8. And we're going to divide that result by 4.399. And yep, we're going to get a better number here. $40 minus 32.8, enter, and divide by 4.399. I get 1.637. I'm going to find the 1.637 on my sheet. And I've got 1.637, so we'll go 1.64, 0, 1, 2, 3, 4. 0.9495, is that what people have, 0.9495? So that means everything this way is 0.9495. In this situation, are we wondering the area to the left, or are we wondering the area to the right? To the right, because we're wondering greater than. And so if you subtract that from 1, this area to the right, this is always what you see on your chart. This side is always 1 minus. And if you subtract that, I think you get 0.0505. So there's about a 5% chance in this situation. If you were to look at this, if you grab 80 couples, you're like, well, what's the chance that half of them are divorced? It's actually only a 5% chance because you're asking a half of them, and the rate is 41%. So that's a little high there. I had a friend at camp one time. She had a friend come and visit. They had never met before. But they sat down and started talking that night. And the next day they got up and they announced to us that they were getting married. They said they just hit it off so well. You know what I mean? And we said, you don't have to jump in. They're like, no, we know. Like, we are getting married. Like, you just met us. They're like, I know, but it's like we're getting married. They broke up 2 weeks later. But maybe you want to give that more than just like a 12-hour period. You try the last one on your own. 70% of people living in Minnesota live in a single-family home. We've selected a group of 40 people at random. What is the probability that at least 50% of them live in a single-family home?
I don't have it on my iPad.
One guy.
I will say that for this lesson especially, I really didn't like what I saw in the book for book problems. And so I wrote all these. Hopefully the ones I wrote for your assignment do end up on the chart I think I erred on the side of caution in that situation.
No, this isn't conscious.
Yep, one of each.
When I was gone, Betsy sent me her for.
Actually, I had the same answer. I just can't do the last one.
Wait, is that what you're doing? I'm doing later.
Did you go
I had
to
a
CCon?
let's have it meeting this morning. And then
I did.
I had to like.
I picked up.
Okay, so I always think it's helpful to draw the picture in the end. And that's up to you, but for me, this is what makes the most sense, okay? We would expect that as we have these people together, we would expect that we would expect 28 of them to live in a single family home. Okay, that's the expectation. We're wondering what's the chance that 20 of them? Well, that's going to be greater than 50%, isn't it? And as you can see from your curve, definitely there's more than 50% there. So we just have to figure out the amount here. That's what's on our table. And so I look at negative 2.76. Can somebody tell me what did they come up with for negative 2.76? 0.0012 289. Okay. So in order to figure out to the right, we do 1 minus 0.00289. And Warren, what did you get when you subtracted those? You got 0.99711?
Yeah.
That accurate? So there's a 99.7% chance that that number is in fact going to be greater than 20. Okay. So, good. That's your last bit of learning you have for this unit. I'm going to hand you the worksheet. It's a combination what we did on Friday as well as today. Just a front and back, your class. Are you going to decide to bring the Pascal's triangle back? So, what is probably at least?
Basically only.
That
Because it was like 2 p.m.
I will try to use phrases more than and less. So, without a doubt, there's no word that's going to speak what is different. We gotta figure that out. I'll try to be very.
It was her. It wasn't me. I think it's
I feel like you did good. I also don't.
Yes, so
I'm very sad.
Oh, so you so that's all you get yesterday.
there was no worksheet.
But I only eat
Yes, I did.
I don't remember.
Okay, I didn't even say it. You guys want to ask? Oh, tell us. Tell me, please tell me.
I'm going to work on making this answer key right away.
For what?
But I know how to do it.
What are you talking about?
Oh,
Oh, that you're just thumbs at? I don't think I'm gonna get it. It's like the. Oh, yeah. I was confused because I heard you talk about something, and then I started talking about the multiple one.
That was kind of funny.
So what do you do?
No.
Because we're drawing the marbles.
I forgot what I meant to read it on Friday.
What do you eat? Doesn't make any sense. Well, okay, so like.
What? What?
Yeah, we have one on this Friday and we tried this Friday.
So where's it gonna be Friday? We haven't Yeah, stay here tomorrow.
I'm actually having because I thought it was a practice.
Hey, 24?
No.
I really don't believe. You might not be right, but you might not.
More of the town.
Please don't throw
So
away.
how do we,
I think it's like what and then like the result.
Yeah.
It's always we always have. And then what? No, they don't have it until no, like it's not when they.
I was like,
We also feels different.
well, yeah, I woke up earlier yesterday.
I was really confused.
I woke up early.
And then
That's
yeah,
it's means that we're back an hour.
yeah, we still have it. It's like all normal, like red brick and now they just didn't even do that. And now you have to open your that part's nice, so I don't have to open it. Oh wait, yeah, now you do. I didn't realize that. Yeah. That thing opens fast. I kind of forgot to. And they just did those too.
Yeah, but you just want to be there.
What?
So stressed out.
No, it's not. Wait. No, it's not. It's just
I just think it's cool that this number is well, and like when I was doing it, I was like the book didn't even explain it that way. Oh, how cool. Pascal's triangle. And like I said, because what I was looking for actually was the building of the normal distribution. So like if you, like again, 1, 2, 1, that doesn't exactly look like a bell curve. Well, like when you start to increase the numbers, it really does. And so then when I did, I was like, wait a minute, you can't all these numbers are, yeah.
He's very short.
It's everywhere.
I was at.
I saw you this morning.
Yeah.
I'm aware.
Yeah, he's aware.
He's gonna jump me. That whole.
What do we do in English? You get a new thing like we did this weekend.
Do we go over the weekend?
Yeah. We didn't finish it in my class. We only did like half of it.
Yeah, we take some notes. Yeah.
I made this. You had to finish the story. So we got the music. And then I finished I didn't do either, but I mean, you remember what to do. Oh, yeah. We can use it separate, you can jump the triggers and do It's like my, yeah, all you do is my.
I didn't think it was that easy either.
No, I thought it was hard.
I just don't think you remember. What? I just don't think you remember like that class because we had it so long. I just don't. I just like. I don't know. I just.
Something that was equal with the math.
His room had nothing in it. It was the whitest lights I've ever seen. His voice was like so nice. And I had to do MCA testing the last week. Oh yeah. And then you can hear everyone on the science test taking away right now. And I was like, why are you all
I'll pull it up right when you got there. The last time. Yeah. What was that shit I was talking about there? This was
No, I know, but that's what I Yeah, because he doesn't have
I'm a good tester. I'm a good geography when it doesn't come to like everything I've ever wanted. You know what I mean? Like, I don't think I'm very good at MCA. Like, I'm very good at math testing. Like, I'm really interested in growth technology and like testing. Yeah. I would rather continue to do a project. And I was